Students of B.sc Part 1 and respected listener, a very good afternoon and welcome all of you to today's lecture. Students of B.sc Part 1, I will teach you today about the kinetics of second order of reaction, a very special topic I have chosen to you for all the students of B.sc Part 1 as well as those students who are preparing their various competitive examination based on engineering and medical, as well as the topic I have mentioned on the blackboard, the kinetics for second order of reaction. The kinetics for second order of reaction, which is actually selected from B.sc Part 1 from paper 3 physical chemistry, chosen from that is of unit 5th titled as that is of chemical kinetics. Students of B.sc Part 1 based on the kinetics of second order of reaction in various competitive examination, general awareness for science branch, engineering and medical and B.sc Part 1 paper 3 physical chemistry. In these various competitive examination and various important examination based on the numerical theoretical part ask and set in these various competitive examinations here. Students of B.sc Part 1, the discussion, the derivation, the explanation, the kinetics for second order reactions based on our previous 5 important postulates which we have delivered in the classroom for first order of reaction and zeroth order of reaction, in which the discussion, the descriptions for any kinds of reactions based on 6 important factors, in which we have in our previous video we have explained. First postulate was mainly concerned to the derivation of rate equation or rate law. Rate equation will be derived by means of 2 its further kinds. First one, that is of differential rate equation. Second one, that is of integral rate equation. Second postulates under the influence of chemical kinetics will be delivered, will be explained by the graphical, that is of representation. Third one postulate was mainly concerned to determine, to calculate the value of half-life periods. Next one postulate was mainly concerned based on that is of Wilhelm equations. Next one, furthermore, postulate was mainly concerned depending upon the calculation of that is of dimension and unit for particular as per concerning of velocity of the reaction or order of the reaction. On next one, the postulate, furthermore the postulate was mainly concerned for the numerical problem solving and its specific example. So on the behalf of our previous 6th postulate, now it is the turn to explain, to deliver today's the kinetics for second order reaction on the behalf of the same postulates as we have delivered in the classroom. We have explained the necessarily fundamental kinetics. First of all, let us turn one by one. That is the first postulate, that is of derivation of rate law or rate equation for second order of reaction. But before proceeding of today's lecture, it is also essential to define that there are 2 types of the second order of reaction. Case first, that is of when the concentration of all the reactants are the same or all the concentration are present in the same quantity here by nature, by all means. Second one, when the concentration for second order reactions are using in different way or different concentration. So on the behalf of that is of case first and that is of case second, one can explain the derivation and rate equation for second order of reaction. Once again, under that is the 2 case, one can derive the rate equation and rate law for second order reaction. Case first, when the concentration of both the reactants are the same. Second one, when the concentration of both the reactants are that is of different. Let us try to understand these two cases, case first and that is the case second, one by one. In case first, on the behalf of important features, that is the first one, the derivation of that equation which will be derived further into its further that is of two subkinds, differential that equation form and integral that equation form. The first one, let us choose a common example of chemical reaction by the consideration of the case 1 in which both the reactant present here in equal in nature, or in other words, when we are taking the concentration of both the reactant are the same, by means of under two different temperature, under two that is the timings here, t is equals to 0 and t is equals to t time, we take that is of initially at t is equals to 0 time, we take a mole per liter, and next one that is of a mole per liter. So obviously when t is equals to 0, we are using here, we take here two types of the same concentration for both the same reactant in such a position at t is equals to 0, the zero concentration of product will be produced here. I mean no quantity of the product will be produced here. Now in next that is of timing t is equals to that is of t timing here, when x that is of degree of dissociation is now reacted in the form of to produce that is the product, since 1:1 or same concentration we are using here. So in the next that is of A minus x, the same x amount on x mole will be that is of dissociated in that is of degree of dissociation to produce that is of twice mole of x. Hence at t is equals to t timing we express two types of the concentration, A minus x first regarding to first reactant A, next one that is of A minus x to produce that is of as per fundamental progress kinetics of the reaction, twice mole of x is now formed here, produced here. Now by using here the next that is of Woodwork or Barge's law, or that is of the law of mass action. The law of mass action is directly proportional to, the rate is directly proportional to the total number of moles and its unity power and its multiplication. Present concentration in the form of active mass is directly proportional here, that is of 2. So in order to solve further, minus d upon dt inside that is of A minus x directly proportional to A minus x to the power that is of 2, 1 A minus x to the power 1 A minus x to the power 1, because it is a well-known example of second order reaction when we are using here that is of the same concentration A minus x. We remove here a proportional, we require a newly constant here which is replaced by that is a K2, negative sign here denote here. Since as reaction move in forward direction, the concentration of the reactant decreases here, so obviously negative sign will be used here. Hence minus d upon dt A minus x directly proportional to A minus x square minus d upon dt when we multiply inside of the quantities of the bracket. A minus x is equals to K2 A minus x square here minus dA upon dt, next one that is of plus dx upon dt multiply is equals to K2 A minus x square here. So differentiation of any constant quantity is expressed as that is of 0 plus that is of dx upon dt is equals to K2 A minus x square, dx upon dt is equals to K2 A minus x that is of square here. Here equation number 1 is now we have derived in the form of first achievement for second order of reaction in the form of differential that equation we have derived here. It is our first achievement. For the kinetics for second order of reaction here, dx upon dt is equals to K2 A minus x to the power square, that is of same equation number 1 here. One important instructions I give to all of the students B.sc part 1 here in this term, how will you calculate, how will you derive, how will you apply the Woodwork or Barge's law for any kinds of reaction. At this step, students get confused here. Students of B.sc part 1 very simple formula to represent, to show the Woodwork or Barge's law, the law of mass action here. For any order of reaction, here we are using second order of reaction, double concentration will be used here. In the right hand direction, you have to express here, you have to write down here. In left hand direction, choose one, either for first order of reaction, third order of reaction, or second order of reaction. Double concentration for second order of reaction, and for third order of reaction you have to write down here triple concentration A minus X, A minus X, next A minus X, in that is of 3 times. In left hand direction you have to choose, you have to write down only that is of a single concentration. It is very simple, student. You should not be to take any kinds of stress in your mind here. In left hand direction use negative sign with that is of differential form. This negative sign denote for the concentration for that is of reactant. Obviously reactions move in forward direction. So in such a position the concentration of the reactant decrease here, the negative sign will be used here, and for mathematical operations here d upon dt will be used here. But here for first order reaction you have to write down single concentration in terms of t is equal to t timing here. For second order of reaction you have to write down double concentration. Here I am using here A minus X to the power 1, A minus X to the power 1. Suppose we derive the derivation rate law for that is of a differential equation or in any kinds of integral rate equation, then you have to write down here that is of a concentration as a sequence A minus X to the power 1, A minus X to the power 1, and next A minus X to the power 1 for that is of a third order of reactions here. So there is no problem for derive the differential or integral rate equation here. Now let us to solve here. 0 plus dx upon dt is equals to k2 a minus to the power square, dx upon dt is equals to k2 a minus to the power square. Say equation number 1 here, where k2 denotes that is of a second order of rate constant here. In order to solve, in order to produce the integral rate equation here, now let us start from equation number 1. Dx upon a minus x square is equals to k2 dt. Now on integral of equation number 2, integrate dx upon a minus x to the power square is equals to that is of k2 integral that is of dt, because k2 is a constant, to take out, remove that is of k2. Or on solving this one, a minus x to the power a minus 2 plus 1 and a minus 2 n plus 1. N here denote here by the integral mathematical just integral and differentiation process just reverse with each other. So n plus 1, n is equal to minus 2 plus 1, minus 2 plus 1 here. Then here the next one that is of a to give the value of 0 value, and its that is of differentiation that is of minus 1 here. So is equals to k2 integral t plus c, c denote here that is of integral constant here. On solving here and on arranging here, 1 upon a minus x is equals to k2 t plus c. Here c here denote here that is of integral constant here. In order to get the value, in order to find out the value of integral constant here, let us apply its fundamental term and conditions. T is equals to 0, x is equals to 0 in equation number that is of twice a here. 1 upon a minus 0 is equals to k2 into 0 plus c. To c to have the value of 1 upon a, it is that is of equation number that is of 3 here. Now put down equation number 3 in equation number that is of twice a. Here that is of twice a, this one equation twice a. 1 upon a minus x is equals to k2 t plus 1 upon a. So that is the equation number 4. So on solving here, on transferring the principal that is of quantities here regarding to concentration, and that is of timing here, k2 t is equals to 1 upon a minus a 1 upon a minus x minus 1 upon a. The k2 is equals to, on solving here, 1 upon t x upon a into a minus x, equation number 5. Here second achievement regarding to that is of kinetics for second order of reaction is now derived, that is of as in equation number 5. Equation number 5 is known as that is of fundamental and that is of real integral rate equation in terms of that is of integral rate equation in the form of rate equation is derived here in the form of that is of integral rate equation here. Here equation number, this one you know here, this one equation number, that is the 1 DRE differential rate equation here. And next one, that is I have mentioned here, equation number 5 integral, the integral rate equation is this one, that is the equation number 5 here. The next one form of rate equation I have derived here. Equation number 5 is the marvelous, very important expression, rate equation for second order reaction when all the concentration of the reactant in case 1 are using, which you are taking in the same concentration are present in the same in nature, by means the same nature or concentration of all the reactant are the same. So in such a position, equation number 5 will give to us the integral and standard, that is the rate equation. Whole on the behalf of equation number 5, one can express, one can study the progress and the kinetics for second order reaction. In coming timing, we will calculate, we will proceed equation number 5 in terms of the calculation of half-life period here. Now till then, now let me allow to me to join to tomorrow the next lecture, and now you take care. Till then, thank you very much.